In this video, we will see fundamental theorems in linear algebra, in particular theorems in subspace of a vector space. A subset W of a vector space V is called a subspace of V if W is itself a vector space under the vector addition and scalar multiplication defined on the vector space V. Here W is the subset of V. W contains the 0 vector of V. W also contains the sum of two vectors. W also encloses the scaled vectors of any element of W. So it satisfies all the 10 axioms of the vector space. So W is a subspace of V. In this example, W is a subset of V, but it is not a subspace of V, though 0 vector of the vector space is an element in W. For some choice of K, the scaled vector is not lying inside the set W. Also, U vector plus V vector is not lying inside the set W. Therefore, W is not a subspace of V. Theorem 1. A subset W of a vector space V over the field F is a subspace of V if and only if the following three conditions are satisfied. Condition 1. For each U vector and V vector in W, the vector U vector plus V vector is in W. Here, plus denotes the definition of vector addition defined on the vector space V. If for each U vector in W and for any scalar K in the field F, the vector K U vector is in W. Here also the scalar multiplication defined is same as the one defined on the vector space V. Subset W contains the 0 vector of the vector space, that is 0 vector belongs to W. If these three conditions are true for any set inside the vector space V, then that subset is called as a subspace. Also, any subspace of a vector space holds these three conditions. Let us prove this statement now. The proof for this theorem goes in two parts. In part 1, let us assume that the subset W of a vector space is a subspace of V, and we have to show that the three conditions A, B and C holds in W. Since we have assumed W as a subspace of V and we know that any subspace is itself a vector space, therefore W itself is a vector space. It means all the 10 axioms for vector space holds good in the subset W. So condition A, B and C are precisely the closeness axioms of vector space. So we have shown when we assume W as a subspace of a vector space, then the three conditions are holding good. In part 2, let us assume that the three conditions hold in the subset W. And we have to show that the subset W of a vector space V is a subspace of V. That means we have to show that all the 10 axioms for the vector space is satisfied by the subset W. Proof. We have to verify that the subset W satisfies the 10 axioms of vector space. So from our assumption, the first condition U vector plus V vector belongs to W implies that the subset W satisfies the axiom 1, that is closeness under vector addition. The condition B, K U vector belongs to W implies that the subset W satisfies the axiom 6, that is closeness under scalar multiplication. Assumption C, 0 vector belongs to W implies that the 0 vector of the vector space V is in W. From the condition B, if we choose the value of the scalar k as in particular -1, then we will get the negative element for all the elements of W. That is, minus u vector, the negative vector of V, is also in the set W. So we have shown axiom 1, axiom 6, axiom 4 and 5 are true for the subset W. In the similar way, we can show that the remaining axioms are also holds for all the elements in the subset W. Hence, the subset W of a vector space is a subspace of V. So, this theorem is the powerful theorem which we quite often use to check the subset we have chosen in the vector space is a subspace or not. This theorem tells us no need to check all the 10 axioms for the vector space. It is enough to check the closeness under vector addition and closeness under vector scalar multiplication. Because if these two axioms holds true, all other axioms will be inherited by the subset W. Theorem 2. If W1, W2, etc. WR are subspaces of a vector space V, then the intersection of these subspaces is also a subspace of V. Let us prove this statement. Let W be the intersection of the subspaces W1, W2, etc. WR of the vector space V, and we have to show that W is a subspace of V. We know that if W is a subspace of V, if and only if all the elements of W should satisfy the 10 axioms of vector space. Instead of checking 10 axioms, we can check closeness under vector addition and closeness under scalar multiplication. That is, we have to show that u vector plus v vector belongs to W, k u vector belongs to W, and 0 vector is in W. If these three conditions are true, it indicates W is a subspace of V. Let us check whether W satisfies these three conditions or not. Let W equal to W1 intersection W2 intersection etc. intersection WR. Now we have to check whether W is a non-empty set or not. The set W is non-empty because W1 is the intersection of all subspaces, and for a subspace 0 element must be a member. Therefore, W1, W2, etc. WR contains the 0 vector of the vector space V. So definitely their intersection also contains 0 vector. Hence 0 vector is in W. Secondly, we have to check whether W is closed under vector addition and scalar multiplication. For this, let us choose two elements in W, u vector and v vector. If we pick an element in W, it means it is an element in each of the subspace W1, W2, etc. WR. Now, W1, W2, etc. WR are subspaces of a vector space. Therefore, they are all closed under vector addition and scalar multiplication. That means u vector plus v vector is in each of the subspaces W1 to WR. Similarly, for any scalar k in the field F, k times u vector is in each of the subspaces W1, W2, etc. WR. Therefore, it follows that u vector plus v vector is in W, k times u vector is also in W. Hence, W is closed under vector addition and scalar multiplication. Therefore, if W1, W2, etc. WR are subspaces of a vector space, then their intersection is also a subspace of the vector space. Hope you are comfortable in deriving this particular theorem statement. Now a question for you. We have shown intersection of subspaces is again a subspace, right? Now think about the union of subspaces is again a subspace or not. Similar argument you can give and check whether the union of subspaces is again a subspace or not. Theorem 3. The solution set of a homogeneous linear system Ax equal to 0 of m equations in n unknowns is a subspace of Rn. Let W be the solution set of the system Ax equal to 0. And we have to show that W is the subspace of Rn. In order to show W is a subspace of Rn, we have to check whether 0 vector is in W, x1 vector plus x2 vector is in W, k times x1 vector is in W. Let W be the solution set of the system Ax equal to 0. We will pick two elements in W, x1 vector and x2 vector. If x1 vector belongs to W, it means x1 vector is the solution of the system Ax equal to 0. Therefore, Ax1 is 0. Similarly, if x2 is in W, means x2 is the solution of Ax equal to 0. Therefore, Ax2 equal to 0. Now we have to check whether W is a non-empty set or not. Here W is a non-empty set because for the homogeneous linear system 0 is a trivial solution. Therefore W contains 0 vector always. W is a non-empty set. Secondly, we have to check whether W is closed under vector addition. So consider A times x1 vector plus x2 vector. This can be written as A times x1 vector plus A times x2 vector. Since x1 vector and x2 vector is in W, Ax1 vector is 0 as well as Ax2 vector is 0. Therefore, x1 vector plus x2 vector belongs to W. Next, we have to check whether W is closed under scalar multiplication or not. Consider A times k x1 vector. K can be any scalar in F. It can be written as k times A x1 vector. A x1 vector is 0 because x1 vector is in W. Therefore, we got A times k x1 vector is 0 vector, that means k x1 vector belongs to W. Hence, W is a subspace of Rn. The solution set of a homogeneous linear system Ax equal to 0 is a subspace of R power n. Thank you.